This is the third molecular formula where we're looking to draw a Lewis structure, a valid Lewis structure. Consider the geometry and also consider the polarity. So let's get started. The first thing we always do is determine the number of valence electrons. So with nitrogen having 5 valence electrons, again because it's 5 steps over, counting lithium and moving to the right. Well, we have 2 of them, so we'll say 5 times 2 plus our 6 for oxygen times 3. So what does that give us? 28 valence electrons that we have for N2O3. Nitrogen again is further to the left than oxygen, so it has a greater need for bonding. It likes to have 3 bonds, so we're going to just say this is our middle, our center for the frame. And then we add in the 3 oxygens, and we don't have to worry about picking a particular side. We can just say that there's 1 on one nitrogen and 2 on the other. I could have put this on the south side. But then we know that we have 8 electrons already present within the frame, so we need to add in some more. Add in the other electrons, which would be 20. We need to add in 20 more. So let's do that, and we do it from the outside in. So we're going to work on the oxygens, kind of do that 2, 4, 6, 8, who do we appreciate thing. So we need to add 20 more, so 2, 4, 6, 8, we stop there. 2, 4, 6, 8, 10, 12, 14, 16, 18, and now because I'm needing 2 more, I'm going to put them on this nitrogen here, because he only has 2 bonds off of him. This has 3 bonds off of it. So I chose this nitrogen because he needs the electrons more. But I think we have them all. 28. There's 8 here. 10, 12. That's 20 with these, and then 28. So we're good in terms of our getting all electrons in. And remember, it's at this point that you have to say, okay, everything that's going to be done from this point on is within this construct. So I'm going to just work with this to drop things down, and we drop down our lone pair electrons to satisfy the nitrogens. We need to, because this nitrogen has only 2, 4, 6 around it, so I'm going to go ahead and drop this down for sure. So that's not there's no resonance forms, it's just we have to move to make that double bond. On the other nitrogen, it can go either way. We can come from the north and give this nitrogen 8 electrons around it because he only has 6, or we can come from the south. I'm just going to draw it from the south, but we could as easily have considered the resonance form where we have the double bond here. Alright, now we've satisfied the nitrogen in both this one and this one. It has 8 electrons, but we notice though he has 8 electrons, he has 4 bonds. So that's 1 more than what he likes, so he's going to have a positive charge, this one on the right. The one on the left does not have a positive charge. He has 3 bonds, so he's happy. This oxygen does not have a charge, but this oxygen has a negative charge. We know that because he has 1 less bond than what he wants. Oxygen likes to have 2 bonds off of him. So we have now, I think, a final structure that looks good. We're just going to now need to talk about geometry and polarity. So the geometry around these 2 nitrogens is the same. We would say as far as the count, it's 3. Because we have 1, 2, 3 atoms off of this nitrogen. We have 1, 2 atoms off of this nitrogen plus a lone pair. So they're both trigonal planar. This would be trigonal planar because we have a 3 count off of it. 1, 2, 3 atoms off of this one. 1, 2, 3 things, 2 atoms and 1 lone pair off of this nitrogen. Okay, one last thing, we need to look at polarity. Now when you have a zwitterionic state or positive and negative charge within the structure, And again, this negative charge would really be split between two atoms, not just on this one. It'd be minus 1/2, minus 1/2, because we have resonance at play. This is being a resonance form, but we can have the negative charge here also. So really, the polarity would probably, as far as the overall polarity, would be towards these oxygens here, because you have a formal negative charge and you have a formal positive charge. And anytime you have a formal negative and positive charge that's not symmetrical, you're going to have a dipole moment. You're going to have a difference between the center of the negative charge and the center of the positive charge. So we have a dipole moment. There's polarity within these bonds, of course, because they have formal charges. Formal positive charge and the negative charge is split between these two oxygens. So the dipole moment would probably be towards those oxygens. All right. So we've looked at drawing N2O3. We've looked at setting the charges, and that was helpful for us also, along with knowing that it's trigonoplanar, to knowing that we have probably a dipole moment in the direction of the two oxygens off of this nitrogen. We'll do one more, and then we will be done with sort of a review of drawing structures from molecular formulas.